All right, I have to be careful with OBS because sometimes I type over that screen and ended up, stopping the recorder. That happened with one of the classes. I think it's this class on Tuesday. That's what happened. I actually got a very short recording at the very beginning, and then somehow, the recorder stopped. I think I might have just, kind of the mouse went over that particular screen, and I was typing something that turned out to be the keyboard command to stop recording. So it's good right now. Okay, it's recording right now. All right. So let's go ahead and get started with the implementation of Traverse. So before I get started, are there any questions or any comments about the implementation of this program? No particular question. Okay. Was it difficult? Was it kind of easy? Was it just somewhat tedious, but otherwise not too difficult? How would you guys rank it? Okay, all right. Anyone else? Mm-hmm. Debugging the recursive part. Okay. So I'm gonna erase this program here and then start from scratch. Okay, because I don't want to just use a known solution. So I'm gonna delete the entire thing and then start from scratch. Okay. So we do have the entire class period today, which is 80 minutes to work on this program. So if you guys want me to work on it step by step, like just verifying each step is working first, I can go that route. Or if you want to just look at the entire implementation and then kind of have some time, maybe at the end of the class, to take a look at very specific problems, we can do that too. So which way do you want me to do it? How do you want me to do it? Step by step, kind of with verification in between, or do you want me to just write out the entire thing? Step by step? Okay. All right, so we'll go step by step, which means, in the C code, we're gonna go by stages. So if you watch the video, there are a few suggested different stages, and the first stage is just like this. Okay, it's not going to compile in C because there's no halt statement in C. Okay, so the halt is only here to illustrate. Okay, we'll just go ahead and stop here in the assembly implementation just to make sure that we have the conditional statement implemented correctly. Now, having the conditional statement implemented correctly is really important as a first step because that's how the recursion is going to stop. Now, in order for the recursion to stop, we need two things. One is the conditional statement has to be implemented correctly. Two, you have to pass pointer correctly as well. So in other words, when you're supposed to be passing a null pointer and you're passing something that is not null, then the recursion is not going to stop. Okay. So one thing at a time, we'll make sure that if you do pass a null pointer, it does stop first. So that's the first thing we need to check. All right. So on this side, we're going to go define all the usual labels. LVS is 0 because traverse has no local variables. And then traverse, the first parameter, which is PTR, is traverse LVS 1 plus. This 1 plus has to do with the byte that is used by the return address. So that's why, at the frame of traverse, um, where we can find pointer PTR is 1 byte from the base of the frame. So it really it might be helpful, even in the final exam, to draw a frame for a particular function based on the C definition. In this case, the C definition has no local variable, which means the very last thing that is pushed by the caller is the return address. And that's why the return address is sitting at offset 0, which is at the base of the entire frame. We have no local variables. And then we have pointer, which is the first parameter, and an offset of 1. And then we have p array sitting at an offset of 2. But this is the frame of traverse. So understanding the structure of the frame, which part is constructed by the caller, which part is constructed by the callee, and overall, what does it look like, and the offsets to each item in the frame is very important, in your final exam. Okay, and it is kind of important with traverse, but because traverse has no local variable, so it is actually more of a simpler case, when it comes to the construction of a frame. So now we have the second parameter, which is p array, and I'm going to have to decline the incoming call. Okay, traverse ptr 1 plus. Okay, and I thought there we go. All right, so now we have the offsets. So with the offset definition on lines 15 to line 17, we have labels. Basically, the label traverse LVS is just 0, which is actually the offset to the return address. But we really don't care because the return address is not something that you need to access inside the function in C, so it does not really need a symbolic name. Traverse underscore PTR is really just one. It's just a symbolic name of one. And then traverse underscore P array is really just a label or a symbolic name of two. So this way, I don't have to keep track of who is one and who's two when I'm writing the program. I just refer to the label name. And then what we want to do is the best way to approach local variable is just pretend that you always have local variable. So you basically just go like, okay, we are always going to allocate even though there is none in this case. Subtracting 0 from the stack pointer doesn't do a single thing to the stack pointer, right? So it is redundant. It does consume some additional execution time, but from the perspective of is this wrong? Nope, it is not wrong. Okay, just in case we do have local variables maybe later on, I don't have to change this part of the program. And for the same reason, I'm going to do the deallocation, even though there is nothing to deallocate. But I would also usually just write the exit code, which is LD BD, increment D, and JMPB at the end here. So when you're studying for the final exam, which is next Tuesday, it is important not to just recognize patterns and go like, okay, these are the three instructions that we need when we return to the caller. You always have to remind yourself why those three instructions and why in that specific order. What is each instruction doing? And how does it relate to returning back to the caller? So you always have to remind yourself those concepts of returning to the caller. All right, so now with that done, I'm going to implement the conditional statement. The conditional statement is really just checking whether pointer is null or not. So what I'll do is I'm going to load register A with traverse PTR, which is an offset, add AD. Now register A has the address of pointer, which is not what I want to check because I don't see the ampersand operator here. So that means I need a value. So I need to load AA. So at this point, register A has the value of pointer. Now you might say, but pointer itself is containing the address of somebody else. You are correct. But at this point, we just need to know what is in the parameter pointer, regardless of what type it is. So it can have a type of unsigned integer, it can have a type of pointer. It really does not matter. I just need to know whether it is 0 or not. Okay. So now we can do a compare. You can do a CMP, okay, but CMP A0 does not work, okay, because 0 is an immediate value. Compare can only work on two registers. And that part has to do with the architectural limitation of TTP. It simply does not have a pathway to allow you to compare to an immediate value. So that means, okay, that's kind of a chore. But the easier way to do this is to use AND AA. Okay, this was illustrated in um, the program to find the absolute value of a particular register, register A actually also in that case, because this is forcing the value of register A through the ALU and affect at least the Z flag and also the S flag. So those two flags are always affected by anything that goes through the ALU, with the exceptions of increment and decrement, which by design do not affect the flags. All right, so after the end, we can now do a JZI to get to the end of the conditional statement. So I'm going to call the label traverse. I keep misspelling traverse here. And if 0, because we have only one single conditional statement here, but I'm just going to call it the first conditional statement. And this is a very systematic way for me to label the names um, of certain points of a control structure. So this way, the name of the label implies what it is and how it corresponds to the C code. And typically, the way I do things is as soon as I do make a conditional branch, I would also define where the label is supposed to be, which is going to be here, and in between is going to be the then branch. So this is how I usually do things. Okay, now whether you do it this way or not, that's up to you. But I do things usually by structure so that I don't forget to end a structure when it needs to be ended. The commenting is also important because if I do things by structure, which means if I open parent, I always close the parenthesis first. That means I also need to know, okay, where is the middle part of this thing and what does it mean for me to be here? And that's why I have that comment on line 28. So right here, I can already put in the two halt instructions. This halt is corresponding to the halt in C on line 13, which is when pointer is not null, I would halt at this instruction, and I can even comment this and say stop here if and only if PTR is not null. And then I should stop here instead. Okay, stop here if and only if pointer is null. So that's my first program to test because I just need to know whether the conditional statement itself is implemented correctly or not. Do we have any questions about this part? Okay, all right. So now we give it a test. Okay, so I can now use the regular Reefer Spider because yesterday I had to use the secret Reefer Spider so that nobody else can actually see it. But today is the due date of this task too, so I can use the other one. Alrighty, so let's maximize this. And I have not submitted it yet. So submit. This is traverse.ttp ASM. And let me make sure that I have indeed saved the code. There we go. We save it. And I'm going to move this tab over to be next to the River Spider tab, just so that it's easier for me to find it. So the way I write this code is not going to be helping you because you don't have any additional programs to turn in. However, the way I analyze and the way I construct a program can still be helpful if you want to create a checklist of, okay, how do I check whether this TTPSM implementation is consistent with the C code? So um, all right, so we go back to the assembler and try to find out whether it does the right thing or not. It should stop at the halt instruction. The question is, which one does it stop at? So this one stopped at the halt instruction that says stop here if and only if pointer is not null. So we want to go back to the assembly code because I cannot remember what I passed to traverse to begin with. So in the main program, which is given to you already, in this particular case, I passed N1, the address of N1, which is not null, to traverse. So it is correct to end up at a label where it says, okay, stop here if and only if the pointer is not null. So it is correct. But I need to check the other one too. In other words, to make sure this code is not wrong, I also need to check whether it will stop at the correct halt instruction if I give it a null pointer. So I'm just modifying this line. Now, the better way to do this is to comment out the original line, make a copy of that, and then change that. So this way, if I need to revert it back to what it was originally, it will be easy for me to do. So save the program, go back and rerun the Reefer Spider so that I can double check. And this time, okay, is it already updated? Or did I save the program? Let me see. Oh, okay. I use uppercase W, which is not a command, so I did not actually save the program. There we go. Do it one more time. So this time it should stop at the halt instruction, where it says, stop here if and only if the pointer is known. Okay, so we'll double check. So yes, it does stop, stop here if and only if pointer is not known. So I got this part done. Is that okay? Now, this is a very important first step because without this step done correctly, you don't even know whether your program will correctly terminate, even if you are to pass all the parameters correctly, because the conditional statement may or may not be working. This way, I know that it is working. Okay, if I pass a null pointer, it will not perform whatever is in the then portion of the code here. So it will just stop the recursion and it should stop going backwards. All right, so with that tested, I'm going to change this back to the original one, which is passing the address of M1, so that I can continue to go back and write the code over here. So if I were using revision control, like get or CVS or just RCS itself, I would have created a revision of this program right now at this point. And I would have commented and say, okay, this program works, and I have it working up to the point where um, I have implemented the conditional statement. Okay. Um, how many people know what I'm talking about? What is a revision control program? Okay, very good. Do you want to explain that just a little bit? What it does? Yep. So you can go back and you can compare. So you don't always have to just go like, oh, okay, I'm just giving up the current version. You can always compare to an earlier version and find out what differences you have made or what modifications you have made. Because most of the time, it is just one or two modifications that are not good that is causing the program not to work anymore. So you just have to look at the differences, compared to a previous one. And there are other tools too, but Get is the current industry standard. So it is helpful to learn how to use Get, or at least how to use GitHub, which is based on Get. Okay, you can use Get as a command line tool without internet access. Okay, so that's actually a pretty useful tool by itself as well. All right, so with this done, I'm gonna take this out, and then I will try to implement the second version or the first stage, the second stage of Traverse. Okay. So if this was the Kung Fu Panda movie, this was level 0. Okay. I know most of you cannot recall, specific lines from the movie, but there was one time, when Sifu, basically said, "There is now a level 0." After Po got beaten up by the training room and yeah, set on fire and got beaten up a little bit. All right. So now we look at Traverse 1, which is level 1. Oh, that's a C program. Traverse1.c. There we go. Okay, so Traverse 1 is taking out just the recursive calls, but it has these two in it. So these two statements on line 14 and line 15 of the C code is probably more complicated than the recursive calls themselves. Now, the recursive calls themselves are harder to debug because it can potentially lead to an infinite loop, quote unquote infinite loop. It would chew up the stack, then it will work itself into the code until it corrupts the code to the point where the program stops execution. That's what it would do when the recursive calls are not done correctly. But in terms of complexity, line 14 and line 15 are actually more complex, but they're easier to debug. So there's a interesting contrast between something that's actually easy to implement but difficult to debug, as opposed to something that is difficult to implement but easy to debug. The reason why this is difficult to implement is because, oh, this is a double dereference and we are incrementing something that is pointed to by something else. That makes it a little bit difficult because you really have to keep track of what is in this register now, okay? Because now you have to differentiate between the offset to an item on the frame, the address of something on the frame, the actual value of something on the frame, or something that something on the frame is pointing to, and so on. Okay, so you really have to keep track of all of those things in order to implement line 14 and 15, effectively. But it's easy to debug because it does not lead to an infinite loop. So all you need to do is to compare the outcome of running the assembly code against the outcome of running the C code. Okay, I believe in the video, I also talked about what you're supposed to see if you are to run the C code here. Is that correct? I think I did, but no, I did not. You don't remember? Okay. But the C code is runnable, okay, which means you can compile and run the C code and then find out what it does to the elements of buffer, which is in main, and what it's going to do to the local variable p, which is also in main. So those are the side effects in the C code that can be observed also in the assembly code. All right, so in this case, I am going to test run the code in C first, just so that I can see, okay, with this modification, what is it going to do? So we'll go ahead and do a gcc -g -o traverse one and then traverse one.c. Okay, so now we have traverse one, which is the modified version of traverse without the recursive call. So we'll gdb traverse one, and then we'll put a breakpoint at the very end of main. So we'll put a breakpoint on line 32. Okay. And we'll also put a breakpoint before traverse. So we'll put a breakpoint on line 31 as well. So run the program, and now we say, okay, what is in the buffer of main? Okay, we say print buffer. So we get some random bytes here because it's not even initialized. Okay, so we just have to say, okay, the first byte, okay, the first element of buffer is some random, uninitialized content. Okay, just keep that in mind. And we also want to know, where is P pointing to? Okay, P is pointing to basically the same as where buffer is, because that's how we initialize it. That part of the code is already done in the assembly code that I gave you. So this part is already done. So now we continue the execution, which means we end up on line 32, which is after traverse gets its thing done. So now we take a look and say, okay, what is in buffer, particularly the first element of buffer? Oh, it is now a 5, which is the member value of the structure n1, which is a global variable. Okay, so we note that. And then we also want to know, what about p? P is now, instead of pointing to the location 7b, it is now pointing to the location of 7c. So the local variable p of main got incremented. So that's the side effect that we should see. So knowing the side effect of the C implementation, now we can go like, okay, so how do we do the same thing in the assembly code? So in this case, what we need to do is to implement these one by one. The right-hand side of line 14 in the C code is saying that we need to access the member value of the structure that PTR is pointing to. So that means I think we need to get to the value of PTR first, because that is the address of the structure. And we need to get to the address of the structure, add the offset from the beginning of the structure to a member, and then dereference one more time to get to the value of a member of that structure. So that's the usual sequence of code. I don't have to load anything into register A anymore, because register A still has the value of PTR at this point, but I don't want to do a shortcut, because doing this shortcut means the shortcut is not going to work as soon as I implement the first recursive call. Okay, because any call to a function means all the registers will be destroyed. So it's safer just to recompute everything, so that I don't have any dependency on the earlier code. So I will do LDI, okay, traverse underscore PTR to a particular register. Register A is fine. Um, add AD, and then we do a LDAA, okay? So once again, what I said a little bit earlier also applies here. This is a template, okay? Because we look at the same instructions over and over again. So most people go like, oh, I just have to memorize the sequence of instructions. You can do that, but as you do that, also do not forget to understand what each instruction is doing. In other words, after each instruction executes, what is exactly in register A, okay? So I will give you a clue here. The way I would document this is basically the address of PTR minus the stack pointer because it is the offset, right? The offset of PTR is in this case 1. But how do we get to the 1? You can look at it in two different ways. It is one because of the way we construct or the caller constructs the frame. That's one explanation. The second one is that, but on top, we also know the stack pointer is pointing here at the base of the frame, and the pointer is here. So the address of the pointer is whatever address is here, but it is not one. Okay, it is some address. The stack pointer is always pointing here. So when you subtract the address, when you subtract the stack pointer from the address of PTR, you get 1. So that's why, when I want to document it as an offset, I can use this notation here. So uh, what happens when you add D to the whole thing? Okay, this is simple algebra. Subtracting D and then adding D back cancels out. So now what you have left is the address of PTR. And now here, the way why A is PTR is because we are dereferencing the address of PTR. For the most part, you can look at dereference and address of as operations that can cancel out each other. So in this case, the dereference and the address of are canceling each other. So now I just get the value of PTR here. Okay, so it's very, very important to understand what is in a register as you go along with all this stuff here. So now we get to the next instruction, which is LDI-B. I have to use a different register in order to load the offset to value as a member from the beginning of the structure. So the question now is, how do I designate that? There's no easy way to do it. You can simply say offset to the value member, okay? But that's not very specific. So the other way we can do this is the address of um, this thing minus PTR itself. So that's one way to kind of specify what it is, okay? Because it's going to be handy to look at it this way, because once we add B to A, then what do we have in register A? Register A is now PTR plus whatever register B has, which is the address of PTR points to value or the address of member value of the structure that is pointed to by pointer minus PTR. So once again, once you apply algebra, pointer is over here, and then we subtract pointer. So what we have left is really just the address of the member value pointed, the member value of the structure that is pointed to by PTR. Is that okay? So I'm just presenting different ways of documenting and looking at what is in a register at different phases or steps of trying to get to the value of a member of a structure that is pointed to by a pointer. And the pointer itself is something on the frame because it's a parameter. All right. So you look at the C code, and the C code says, "Oh, we don't really know. We don't really want the address of this member. We want the value of this member." Okay, well that means here we just have to do a dereference like so. So now A is okay. Do you guys want me to? Okay, I'll just do it. I'm not gonna ask. Okay, so now we have the dereference canceling out the address of. So we basically end up with really just the value of the member value of the structure the pointer is pointing to. So this is the full sequence explained, with simplified comments. Now in the exam, you can use the same kind of comment if you want to, but you can also just say offset to something. But offset to something can be misleading because we have two different types of offset. if the name of an offset has the name of a structure as a prefix, it is the offset to a member of a structure. If the offset has a prefix that is the name of a function, then it's an offset from the base of the frame to a particular item on that frame. So if it is an offset, in the frame, you should not be adding the address of a structure and vice versa. Okay, so that means you need to understand what you need to add to the offset to get to the actual address of something. All right, so we have the right-hand side. The left-hand side is also a little bit challenging because it is dereferencing twice. It's like we haven't seen any code that is double dereference. Well, if you know how to dereference once, then you know how to dereference twice, because double dereference simply means you are dereferencing the result of another dereference. So whether it's dereferencing once or twice, if you know how to do it once, we already know how to do it. Okay, the swap program is the first one that has an explicit dereference in the code, and we have already talked about that solution when we covered the answer to the swap program. So now we just have to do about the same thing, except we have to pay close attention to what are we dereferencing and what is in the register at that point. So LDIB with traverse underscore p array. So at this point, I'm not gonna really write down the documentation anymore. You might find it useful to kind of comment this program once I make it available, just so that you have some practice of, okay, let me try to figure out what is in the register. This is the offset. This is the address. This is the value. So at this point, register B is the value of P array, which is useful, but that's not telling me where I should store things. I'm not overwriting the parameter itself. LDBB, now we have what P array points to, which is actually specifying this is the address of where we need to store something. So, but in order to store something to where register B is pointing to, we need a store instruction. This is actually the third dereference, okay? The first dereference is on line 37. The second one is on line 38. This is the third dereference. And you say, but in the C code, there's only two dereference. That's because in C code, to make it easier for us to write a code, normally, when you refer to the name of a parameter, you are referring to the value of that thing. But in assembly language programming, to get to the value of something, you have to first get to the address of that something. So that's one hidden dereference that you do not see in the C code. But in assembly code, there's no escape. You have to do the dereference to get from the address to the value of at that address. So that's why we see in C code there are two dereference, but in assembly code there are three dereferences. So now we store A, which is the right-hand side, to that location. If you want to debug the program right now, that's fine. But since this has no control structure stuff in it, we can also just try to implement the next one too. So to implement the next one, I do about the same thing. Register A now has, I could have saved a register from the previous one, but that's okay. We don't have to optimize the code. So this is the offset, this is the address, and then this is the value. Now we have to be careful because the value of P array is by itself a pointer. The statement on line 15 in C says, I am not incrementing P array itself as a parameter. I am incrementing what it points to. So that means it is what A is pointing to after line 43 in the assembly code that I'm incrementing. So in order to do that, the first thing I need to do is to retrieve that. So register B is whatever P array is pointing to, okay? I need to add one to it, which is easily done with the increment instruction, and then store that back to where register A is pointing to. So these 6 instructions from line 41 to line 46 is going to implement what line 15 is supposed to do. All right, so now would be a good time to test it, okay? Make sure it's saved, and then we run it again, okay, like that. And we should now see element 0 of buffer of main to store a 5, to have a 5 in it. And we should also see P of main to have a to have its pointer incremented. So it is buffer plus one, or the second byte. It points to the second byte of buffer, which also means we also need to get a pictorial representation of the entire program. Okay, what does the frame of main look like, and what we're supposed to see in that case. Did I do that in the video, showing you the how the stack is supposed to look like, what location should be changed, in what way? I think. Okay, okay. But I can do it again today too, because I think that's also important. It doesn't help you much with the homework assignment, but the analysis is going to help you with analyzing the code from the final exam. So I think it is still going to be a useful thing to do. So today's date is 2024 12/12. Okay, and we will do the usual stuff. Okay, we'll specify the addresses. This minus one, and this time we need kind of a bunch. Okay, so I'm going to use this much. Decimal to hexadecimal of that. All right. Okay. Now we need to comment what is in each location. This is the return address back from main. In other words, when main is done, it has to return to the entry code, and this is the return address from main back to the entry code. This location, these locations here, okay, there's a whole bunch, will be the local variables of main. How they are allocated is already in the code here because main is already written. So if I were to go forward a little bit to take a look at main, buffer is the first local variable. It needs 5 bytes, and then p is a pointer, which only needs 1 byte. So there are 6 bytes of local variables that I need to allocate. So let's get rid of this, and this is where we were. Okay, there we go. So these 6 bytes, okay, combined also with this byte here, that's the frame from the perspective of function main. So this is the other kind of weird or deformed kind of frame where there are no parameters, okay? Because the top location is the actual return address already. But then we got a bunch of local variables. The local variables are always below the return address because only the callee is capable of knowing how many bytes it needs to allocate. So for the purposes of this, these 5 bytes are buffer, and then this one here is p. So this is p, local variable p of main, and then these are local variable a of main. But I can even tell which one is which one. So that means, okay, come on, let me go here. This is, element 0 of a of, oh, buffer, sorry. This is this of main, and this is buffer 1 of main, and so on, blah, blah, blah. This is your buffer 4 of main. Is that okay? So understanding this map is really important from the perspective of debugging the program, because this way you will know that, oh, okay, so when we call the function, okay, now we are constructing the frame to traverse. So when you call traverse from main, we are pushing the address of P on the stack first. So technically, this is P array of the first invocation of traverse. But the value that we should expect is the address of P, which is FE. The first parameter is N1, or the address of N1. So we'll just say, okay, the name is pointer, but what it is the address of N1, which I'm not really too concerned about right now. So when we increment, or when we store the 5 to where with a double dereference of P array, we are basically going like, okay, P array, tell me where you're pointing to. Oh, you're pointing to FE, cool. And what are you pointing to? Well, that's initialized by the main program to point to the location F9. So that means F9 is the location that is supposed to store a value of 0.5. That's where the 0.5 is going. So that means when we look at the trace of the program, we need to confirm that a 0.5 is written to the location of F9. But there's a second operation. The second line in the C code is going to increment whatever P array is pointing to. So once again, we ask P array, where are you pointing to? Oh, I'm pointing to location FE. This is location FE. And then we say, oh, you're supposed to increment. You should go from F9 to FA. So now we can now use FA over here, and then I will use the strike through method to indicate that the value was F9 and we're expecting it to change to F8. So this is the effect of what I would expect. This is my expectation of what the program should do in the first stage of the traverse program. And until I confirm this, until I know this is done correctly, there's no point in going forward with the recursive call. Okay, so that's the first thing I need to do. So now I need to go back to the command line, make sure this is saved, and then go to River Spider and run it again. All right. I have to say, depending on what you guys did, the exercise of coming up with this map by itself is already studying because you're basically making sure that you have a good understanding of what a frame has, where to find each item, and what the C code, when the C code runs, what does it mean in this particular memory space. In other words, you have to know what your program is supposed to do before you figure out how it is going to do it. Does that make sense? Okay. So when you're studying, you can still put some focus on, you know, first what needs to happen, looking at the C code, and then look at the assembly code and ask how do we use assembly code to make that happen. So that's that connection is always important. All right, so let's go back and check whether the program does what it is supposed to do. Now, you can actually hand trace every single instruction. Are we supposed to push FE to location F8 according to this? Yes. Okay, so we can actually really confirm this step by step and make sure that we got everything done correctly. And then over here, the next push is to location F7. Are we supposed to push 3B to location F7? Well, this doesn't really say, it just says it's supposed to be the address of N1. So how do we know that we just pushed the address of N1? You go to the Assemble tab, and then you just look up where N1 is defined. And I think it's down here somewhere. Down. Here's N1 as a label. And the location of N1 as a label is indeed 3B. So now I have also confirmed that this location is getting the correct value. The next location is going to get the return address from traverse back to main, which is something, but I'm not too concerned about it. All right, moving on with the trace here. uh, Analysis. There we go. So we move on, and then we go like this is supposed to be the return address, but it's not of any concern right now to me because I need to know whether those write operations are indeed happening. So this is the first confirmation that location F9 is getting a value of 0.5. Okay, so that's one confirmation. And then when we go just a little bit further down, we can see also location FE, which is the local variable P of main, is also incrementing from F9 to FA. The F9 is there already before traverse is called because main is initializing pointer P of main to point to the beginning of the buffer. What we need to confirm when we are executing or when we are running traverse is that location get incremented from F9 to FA. So now we have that confirmation as well. Now, we are not quite done with the verification because I actually took out all the halt instructions, which means I'm also should be confirming that this is returning back to main, and the return is happening right here because we can see the jump of the line numbers. It went from line 55 to line 101. So the only reason why it would jump that far ahead is because we are returning from traverse back into main. So now the question is this the right location to go back to? The answer is, okay, let's go back to the source code. There are many ways to double check this one, but I can use the source code to do that. So I go to line 101, And indeed, that is the one instruction after the JMPI instruction in the call. That is always the correct location to return to from the perspective of calling and returning. So I have confirmed that as well. Now, at this point, if you trust me, you don't have to verify any further because the main program should have deallocated everything in the correct sequence. Okay, there we go, undo. So it should have deallocated everything, and then and then we'll go back to the entry code and then halt at that point when the stack pointer is back to 0, 0. Is that okay? All right. So stage one is actually quite important in the overall progress of implementing this program because it is relatively easy to debug. There's no control structure involved in the process. Now, can you mess it up so that it leads to what looks like an infinite loop? It is possible. Okay, if you overwrite the return address itself, it will definitely give you something that looks like an infinite loop. But is it likely to happen? I would say it's not very likely. Okay, so that means this is difficult code from the perspective of, oh, there's a whole bunch of dereference. I have to dereference a bunch of stuff, add something to the result of the dereference, and then dereference one more time. Okay, from that perspective, yes, it is somewhat complex. But from the perspective of control structure, it's not, okay, because there's no loop, there's no conditional statement involved in step one. Are we still doing okay so far? Are there any questions you guys want to ask at this point? Okay, all right. So now we can go back and say, okay, well, now we want to kind of play with the uh, recursive call. So we'll do one recursive call at a time. Now, whether you implement the first one first or the second one first, it doesn't really matter, okay? But I'm just going to implement the first one first, like this. Now, there's one trick, okay, to this whole thing, but that trick has been illustrated before. So I'll identify that trick, when we get to that point. All right. So the first thing we need to push is the last parameter, which is p-array. Now, whether p-array is just an unsigned AB integer or a pointer to an unsigned AB integer or pointer to an AB unsigned integer does not matter, okay? As long as it is a 1 byte thing, we're good because the C code specifies and go like, don't do anything with P array. Just get the value of P array and push it on the stack and call it a day, right? So there's no address of, there's no dereference, there's nothing here. So all you need to do is to figure out how big, how many bytes is P array itself, okay? It's 1 byte because it is an address of some kind and push it on the stack, okay? So that means, okay, boring stuff, okay, traverse p array offset. Now we have the address, and now we have the value of p array. Decrement d, st, da, push it on the stack. Okay, that's it. We're done. Now the second one is, oh, we need to get to member L of the structure the PTR is pointing to. But if you implement the program in the sequence that I recommend, in other words, you have traverse one already done, then you already know how to get to a member of a structure that is pointed to by pointer because we got this already done. It's the same thing or almost the same thing, except this is a different member. But if you just copy and paste the code, it's not going to work, and I'll explain why. So in this case, let's just say that I copy and paste the code. Let me just literally copy and paste the code. Okay, so we'll go like line 38 to, okay, which line here? Because we just need to retrieve it, so that'll be up to line 43, okay? Copy to here. Okay, I just literally copy and paste, okay? And you go like, okay, tag, but you have to remember we are not accessing member PT or member value this time. We are accessing member L. Okay, fine, we'll change this to L, okay? We'll even change all the comments, okay? So this is L. And this is also supposed to be just L. This is supposed to be, okay, I should have done a replace, of value to L, but it's okay. Just a few more lines of changes here. Okay, But we have a problem. We have a problem because we just pushed something else on the stack. Okay, so if you go back to the picture of what is in memory, we have just pushed p array again on the stack at this location. So this is basically just p array itself, which is fe again. Okay, we're just passing p array along to everybody else. But this is p array of the next frame. We are in the process of creating the frame for the next invocation. And because this is the last item that is pushed, the stack pointer is now pointing here. Where is the base of the frame? The base of the frame is here. So that means the stack pointer is no longer pointing to the base of the invocation that we're currently in. It is one byte below where it is supposed to be. So that means the offsets that we calculated earlier, they're incorrect now. Okay. Well, okay, they're both correct and incorrect. It depends on whether you look at those offsets as the offset from the stack pointer to the items that we need to access, or you look at it as the offset from the base of the frame to the items that we want. The base of the frame is always the same. This is always the base of the frame. But the stack pointer can move around. Okay, so at this point the stack pointer is pointing here because we just pushed p array on the stack in the construction of the next call frame, which means, oh, okay, so that means right here we are not really loading member L of where ptr points to on the stack. But let's just say that I did not remember this, okay? And I just go like, oh, okay, we got what we need to push. Just decrement D, store that on the stack, and and then we have to push the return address, which is LDIA dot 6 plus decrement D stda. Now we have everything pushed. JMPI to traverse, and we come back. Oh, I remember we are supposed to undo the two arguments on the stack, increment D, blah, blah, blah. Okay. So let's say I made a mistake and not realize that I made a mistake. Okay. So now how do we debug the program? What is the program going to do and how do we debug it? So I'm not going to project what the program is going to do because that's the whole point of the debugging process. So we'll just go ahead and save this program, which is wrong. And we know how it is wrong, but we'll run it anyway. Okay, so we're going to run it and see what happens. This is the part where the code is relatively simple, but it's difficult to debug because it causes the program to go into quote unquote an infinite loop. It's not really a loop, but it does give you the effect of a loop. So now we go back to the trace, okay, and we go like, okay, so we have verified the program up to this point already, okay, which used to be the end of the execution of the whole program. We are now expecting the program to go a little bit further, but you can see that it just keeps going and going and going, okay? So we know something is not right about the program. Now, the other way you can know that there's something wrong with the program is to think about how many invocations it should go before it starts to return, right? And how do we know that? Well, you can run the C code to find out. Okay. In other words, you basically go back to the C code, okay, and just compile the C code, run the C code, and see how far it will go. That will give you an idea of, oh, we are expected to have this many frames constructed at the most, right? So let's do that first. Okay, so quit. So what I'm doing here obviously is not going to help too much in this class, but I'm hoping that it will still help in your next class, especially if you're going to take CISP 430 sometime in the near future, because that class will involve recursion. Okay, now the kind of bug that you can see or the symptoms that you can see in CISP 430 is not going to be the same as this one, but nonetheless, it is good to know what tools you have available in a debugger to help you to debug recursive functions. So in this case, we have this one, and we can put a breakpoint at traverse itself. Okay, so this is just a shortcut of putting a breakpoint at the entry point of traverse. So every time I call traverse, it will at least give me a chance to look at stuff. Okay, so now we just run the program, and this is the first time, this is the second time, and every time you stop at traverse, you can also use BT or backtrace. Okay, so what backtrace does is it will show you how we got to traverse. So in this case, it tells me that main calls traverse, traverse calls traverse, and this is where I'm stopping at. This is the second invocation of traverse. Okay, and we'll press continue again. This is another traverse, but I don't know how the traverses are stacking up on top of each other. Did I return from one and then call the other one? I do not know. But if you do a backtrace at the entry point of traverse, it will show you. So this is the third time. So the first time when we call from main to traverse, it is passing basically the address of N1. And then the second time, which is the recursive call from traverse to itself, it is passing the address of N2. The third time, it is passing a null pointer to the third time. So we know this is it. Okay, we can see at the most three instances of traverse stacking up on top of each other. Three frames of traverses. Okay, so now we go like, okay, so just to be sure, okay, we press continue again to make sure that there are no further calls to traverse, and there's none. Okay, so we know that we have up to three frames of traverse in assembly code. So we go back to the assembly code, and then at this point, I don't even care about what content should go into each frame. I just know that each frame should have a p array, a pointer, and a return address. This is the second frame, okay? This is the third frame. So if I were to extend the addresses down a little bit, this means the stack pointer should go as low as F0, and then it should go back up again. I don't even care about what values go into those locations. I just know that we should only have up to three frames of traverses on the stack. Is that part okay? So when we go back to the analysis tab, we just look at the stack pointer, okay? Because column D shows you the updates of stack pointer. Oh, we have already gotten past the point of where we're supposed to stop. So now we have to back up a little bit. Now this is something that you can only do with this particular tool, is to reverse the direction of execution. We notice something is wrong at this point for sure, but you can back up. You can back it up to the point where, okay, this is the reason why everything after this is wrong. This is not something that you can easily do with a C program, because in the C program, in the debugger, you can set up a breakpoint. Fine, not a problem. But if the breakpoint is already past the point of where the bug is, there's no easy way to reverse the execution of the program. Okay, so now we just go page up, keep going up until the stack pointer is at least up to F0. Okay, so we go back up, back up, back up, close, almost, and we are there. Okay, so this is the decrement of D, and then we are storing to A, which is the return address from traverse back to itself. Okay, now which recursive call are we talking about? There's only one, right? This is why I suggested take out one of the recursive call, make it a single recursion, because it does make debugging a whole lot easier this way. Okay, so now we ask, what are we pushing on the stack? Are we pushing sensible stuff on the stack? So now we go back up and ask, what did we push as PTR? Okay, this is supposed to be PTR, and we only have 5 struct nodes of the entire program. Okay, none of them has an address of DF. So we know we're pushing something wrong on the stack. Okay, but you can also go back up a little bit further and ask, okay, this one is wrong, but if this is wrong because if all the previous code is wrong too, this is correct. Okay, so in other words, it's pushing p array just fine. Okay, p array is always at pointing to the location fe, so this is fine. But we got the pointer wrong. But the pointer may be wrong because the instance or the frame of this particular invocation had it wrong already. So we have to go back up a little bit further, okay, and ask when did it go wrong? This is the return address, okay, and we are expecting this one is wrong too, because the return address is the last thing that the caller is supposed to push. Pointer is the second to the last thing that is pushed, and pointer has to be one of the five struct nodes that we have, and this is also not one of the five struct nodes. So we know this one is wrong too. So we go like, okay, if that is wrong, that means we have to go back up one more level, okay, and see whether that is also wrong. So now we go like, this is the return address, okay. Yep, so this is the return address. It is a 6C because this is the first invocation of traverse. And then we go back up and go like, oh, this one is right. That looks right to me. 53 is the is a lower address. It does correspond to one of the nodes that we have initialized, and you can confirm that by going to the assemble view and go to N1 and ask, okay, N1, where are you? And N1 says, oh, I'm at location 53. So everything is good. Oh, okay, wrong tab. uh, right here. So everything is good up to this point. So we know the problem is somewhere after this point. Somehow we pushed the wrong pointer on the stack when we set up the frame for the next one. So now we go like, okay, who is pushing the wrong thing on the stack next? So we go back down. We go like here, line 34, you're pushing the wrong thing on the stack. Line 34 says, well, I'm only storing whatever register A has. It's not my fault. Ask the person before me. The person before that and goes like, oh, I'm only responsible to reserve a space on the stack. I have no idea what I'm supposed to push on the stack. It is not my fault. Okay? And then the line before says, oh, I'm only dereferencing whatever A has, and A should have, okay, before the dereference, A should have um what is it again? I'm trying to remember. Oh, wait. Okay, this is fine. Okay, this is not the problem. The problem is further down. So I take it back. Excuse me. This is where it is pushing something wrong on the stack. Because location F4, according to this map here, is supposed to be the address of a node, okay, of a struct node. But DF is not the address of a struct node. How do we know that? Well, we first have to say, okay, where is the program ending? Okay, so now we look at the assemble view and then we go all the way to the end of the assemble view and go like, oh, okay, the very last instruction of the entire program is on location 7.3. So the program itself did not specify anything past location 7.3 in hexadecimal. Okay, fine. Maybe it's something on the stack. Maybe we created a local variable of struct node type, on the stack, and we're passing that along. Okay, that is also not possible. How do we know it's not possible? Because the stack pointer is only at F4. So that means when you look at the memory of the entire processor, okay, the stack is growing down and it is only at F4 right now. The program specification, which is from location 0 and up, it is only at location, what, 7.3, I think? Whatever is in between here is no man's land, okay? That's kind of like a neutral zone. Nobody's supposed to be there. Why would I push the address that is in the neutral zone on the stack? It does not make sense. Okay, so that's another way to figure out, oh, okay, something is not right over here. So now okay, so I was accusing the wrong locations of doing the wrong thing. Okay, so we'll go back and accuse this one first. It's like this one says, but I'm doing the right thing. I'm supposed to store whatever register A to the stack pointer. Okay, fine. I'm supposed to allocate a location. I don't even know what we're supposed to be pushing. Okay, fine. Oh, you are supposed to know what you're dealing with here because I see comments, right? A, after this instruction, A is supposed to be the value of the L member of a structure that is pointed to by PTR. We have 5 of those. Which one has DF in it? None of them, right? So now we go like, wait. So that means even though you did something that is wrong, but you're only doing what you're supposed to be doing, which is the reference A. A is supposed to be the address of the L member of a struct node, but it's not. Okay. So now you go like, okay, whose fault is this? Move up one location here. After this instruction, um, register A is supposed to be the address of a member L of a structure that is pointed to by PTR. But nonetheless, it is supposed to be somewhere that is well defined. So it is pointing at location 6D. So this is where you have to look and go like, is 6D the address of the L member of a struct node? Okay, so we remember this. Okay, we go back to the assemble view, and then we go to location 6 and D, which is here. It's like, no, that is not a struct node here. Okay, this is part of the main program. It is not a struct node. So now you go back to the trace again. You go like, okay, this is wrong too. Then you go back to the previous instruction. Okay, this is correct. Okay, the offset from the beginning of a node struct node to member L is 1. Okay, that's fine. That's not a problem. So you ask this one and ask, did you get something wrong? Okay, and you have to ask, what is supposed to be in register A at this point? What is supposed to be in register A is supposed to be the value of pointer. Okay, so now we go like, okay, where is supposed to be what is supposed to be the value of pointer as a parameter from the perspective of this instruction? So the way we are, where we are at right now is we are looking at this particular pointer here, and it's supposed to contain the address of N1, okay? And N1 is, okay, I'm just looking up where N1 is supposed to be. N1 is supposed to be 5.3, not what the trace is suggesting, because the trace is going like, oh, okay, pointer has a value of 6C. No, 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 it's supposed to be 5.3. So now we go like, okay, so you somehow got the wrong thing too. So now we go one step further and go like, okay, does register A have the address of PTR? Okay, because according to the comment here, after the add instruction, register A should contain the address of PTR. And according to this map, the address of PTR is supposed to be F7, but the trace is telling us that it is F6, off by 1 byte. Okay, then you go like, why are you off by 1 byte? Okay, well, the reason it's off by 1 byte is because we just pushed the second argument on the stack already. The stack pointer is not pointing to the base of the frame anymore. And that's why if you just add the offset with the assumption that the stack pointer is pointing to the base of the frame, everything is now off by 1 byte. Is that okay? So that's the process of debugging a program, in this particular environment. It is tedious, okay? I have to say it is not simple, okay? There's no quick and easy way to figure out that, oh, so we are supposed to add one here. But the process is, well, the process. So what does this tell you? How does this help you in the final exam? You just spent like 2 days, trying to figure out this bug because your program just would not stop, the recursion. How is this going to help you in the final exam? What are you going to add to your checklist, or what are you going to track on your checklist and go like, I need to track these things too when I'm going through the code in the final exam. What do you think you need to track now? Where's the stack pointer pointing to? Okay, so you know where the frame base of the frame is. Okay, and initially after the allocation of the local variables, if that is done correctly, the stack pointer will point to the base of the frame. But if you push anything for whatever reason after that, then the stack pointer is not pointing to the base of the frame anymore. Does it mean it's useless in the calculation of the addresses of stuff that is on the frame? No, it is still useful, but you have to figure out how much of it is at different points of the code, which means every time you see a decrement D, you have to say, oh, okay, the stack pointer just moved. Okay, so if you have any code that needs to calculate the address of something that is on the frame after the stack pointer is not pointing to the base of the frame anymore, you have to remind yourself it's like, okay, before I add the stack pointer to the offset, did I have the right offset here? Do I need to make some adjustments? If I do need to make some adjustments, how much of an adjustment do I need to make? How many decrement Ds have occurred between the construction of the frame to the point where I need to access the item on the frame? Is that okay? So that's the conceptual part. What you need to do to put it into practice is kind of up to you. Okay, what do you want to do to keep track of the stack pointer? You can always just have you know with every line that does a decrement D or increment D, you make a special note and go like, okay, we are doing something with the stack pointer, and then you just try to keep track of where the stack pointer is pointing to relative to the base of the frame. Okay, so that's one way to do it. But somehow you will need a way to do that. Okay. Or you can also do it the other way, which is every time you try to use the stack pointer to help you calculate the address of something that is on the frame, then you go back and see if you have done something to the stack pointer in between. So that's it's up to you to decide how you want to do it. Okay, so with this added, I can now go back and retest the code because this time it should not have that crazy recursion. Everything should stop at location F0 and then should go back up again. All right, so the nice thing is the analysis tab actually track where things are supposed to be. Um, and it is still a F6. Did I save the program? That would be the only reason why I should use an IDE. Well, or I can write a script in Vim. So it's a command in Vim to automatically save the code and then run River Spider. I can probably do that. Should probably do that next semester. So now that is fixed, okay, but we also need to kind of confirm that the program does stop at the right place, blah blah blah. So we're going to take a look at the stack pointer and make sure that by the time it decrements to F0, it doesn't go any further lower, and it doesn't go any lower than that. Yep. Okay. After that, it just kind of goes back up. Okay. So I think we got that bug fixed. So I only got 5 more minutes, but once I get the first recursion done correctly without using any optimization or anything that came from before, the second loop or the second recursion is pretty easy to implement because it's really just copy and paste. But it is important to do it step by step. And if I were using a revision control, I would have created a revision right here and go like, okay, the left recursion is done correctly, okay, and basically star it too because this is important. So now I can copy and paste this code, and we have line 30 to line 53. Yank, that's basically copying to the buffer, and then paste it right before the end of label P. But we also have to remember to change all the references to member L to member R. Okay. And we'll specify from 84 to 86, 84 to 86, change, substitute. All right. So I can, hmm, okay. I'm not going to bother you guys with regular expression. We'll just do it the easy way. I was about to show you guys how to do regular expression and do this kind of in a fancy, really kind of fancy way, but I'm not going to do that. So I'll just kind of say replace all the points to L with points to R. Okay, so we'll do this first. And slash G means there can be multiple replacement on a single line. So we'll do all of those. And we'll also do the underscore. So because I don't know whether this is the only reference to the underscore or the label of the offset, so I'm going to do 81 to 85, 86. And at this time I say replace underscore L with underscore R and dash, slash G, also just to specify multiple replacement on a single line if there are multiple occurrences. All right, so we're all done. And then we just rerun the code. Don't do it right now, okay? But in some time, okay, if you plan to really become a professional developer or software engineer, I think VI is worth the time to learn because it really is a very useful tool. There are lots of plugins that can do a bazillion of things, and it is also programmable in Lua. Okay, so you can actually program your own macro in Lua. You can process your text automatically and do all kinds of stuff like that. So it's a useful thing to learn, but definitely not, when you need to study for final exams. All right. So now we're going to look for all the updates to the locations in buffer. So we are looking for F9, A, B, C, D, getting an update. So this is also where you can use regular expression. So I'm going to go for find, not to replace, just find. So I'm looking for the asterisk symbol, F something, and then the character after F is going to be 9, and then A, B, C, D. Yep, because there are 5 locations. A single equal to, and we don't want to replace it with anything, and we just want to search it in this particular sheet or a specific range in this case, and that's column C itself. So we just have to specify the entire column C. Analysis C. I think that works, maybe. And then we specify search using regular expression, and then we say fine. Nope, okay, it doesn't like the way I specified the range. Fine, we'll specify it interactively. Okay, so I don't need analysis again because you only have to specify the sheet name once. Fine. Okay, find. Okay, location F9 gets a value of 03, 04, 05, 09, 08. Okay, so now we're putting all the correct values into um, buffer. And I automatically know that the P variable in main is also updated correctly because all of these updates are done through local variable P of main. So by checking this, I have also checked that local variable P of main has been updated correctly. So if with this done, I now just have to go all the way to the end just to make sure that the stack is balanced when I exit the program and it is stopping at the correct halt instruction. So we are stopping at the correct halt instruction. The stack is balanced. So, I think the program is working 100% now. And right on time too. I did not actually time or plan anything today. I probably need to redact that part from the recording. That I did not plan or did not time anything. This is just the way it is. Do we have any questions? So use this lecture to help you prepare for the final exam because this lecture illustrates all the things that are important. There are templates, concepts, check things that you need to check. Okay? Create your own checklist. Okay? Because once you have a checklist, then you can say, oh, every time I call a function, I'm going to have to check these things here. Every time I push something, I have to check certain things. Every time I access something that is on the frame, I have to check these things. Every time I need to get to the value of a structure, of a member, of a structure that is pointed to by a pointer, I need to do these things in this sequence. Okay? So the concept of using a checklist can be helpful. Okay? But I will not give you the checklist. You guys have to kind of create a checklist. The process of identifying what to use to create a checklist is by itself a process of studying already. Okay, so before you get to the checklist, you're already studying. So even if you forget to bring your checklist, you probably have everything or most of the things in your mind already, and you'll be doing. I may not be 100% because there may be certain things that you will forget, but you'll still be able to identify a lot of things because if you can create a checklist, that means you already understand the concept, but you just may not remember all the details. Okay. Are there any other things that you guys want me to talk about before I end today's lecture? Okay. When are we having our exam? Is on Tuesday from 8 a.m. Very good. Okay, it's not from 9 a.m. Okay, because the lecture starts at 9 a.m. and some people are basically used to, oh, I just need to get here by 9 o'clock. Well, then that person would have lost 1 hour of the exam time. So get here by 8 at the latest. I would recommend arriving maybe 15 minutes early, just so they have some time to kind of calm down, rest, spread your stuff out, for the exam, and and before we start the exam. Bring writing instruments, okay? Write, pencil, pens, it doesn't matter. If you think colored pencils or markers will help you highlight things, bring those too. It's open book and open notes. Anything on paper is fine, okay? So you can bring along any number of items, okay? You can print out all the modules that I have written. You can print your own notes. You can print all the sample programs and solutions to the homework assignments with you. But remember, the more you bring, the more difficult it is to find things. Okay, so you need to find a way to index the stuff that you're bringing so that you can locate all the items easily. Any other things that you want me to talk about? Nope. Okay. All right. Well, I will stay here for as long as there are students in this classroom to talk about whatever you guys want to talk about. Um, but you guys can leave if you want to. If you don't have any questions for me, then I'll see you on next Tuesday.